Okay, we're ready for section 4.6. This section is on the fundamental theorem of algebra. And I may have inadvertently referred to this particular theorem. I forget sometimes where we're at in the book, and I didn't realize that you hadn't covered this section first or yet. But the fundamental theorem of algebra says that a polynomial function of degree n will have n roots. So that's what we're going to talk about today. So this function right here, because it's degree 4, is going to have 4 roots, 4 zeros. Remember that complex factors always come in pairs. That if 3 plus 2i is a solution, then so is 3 minus 2i. This means that it is impossible to ever have an odd number of imaginary solutions. So if you think about this degree 4, if it has 2 real zeros, it's going to have 2 imaginary. It's not possible for this to have 3 reals and 1 imaginary. That's not possible. Okay, so if you look at, for instance, a cubic function that only crosses the x-axis once, that's the real solution. And then I know it has to have 2 complex solutions because altogether it has to have 3 roots. All right. So let's just jump in and do some examples. I want to find all the zeros of this function, and I know that there's 3 of them. So if I graph this on the calculator, I can see that x equals -3 is one of the solutions. And to find the others, let's just do synthetic division using k equals -3. So again, set up my coefficients of my regular or original function. Bring down the 1. -3 times 1 is -3. 7 plus -3 is 4. -3 times 4 is -12. 16 minus 12 is 4. -3 times 4 is -12. And I get a remainder of 0. That means that x squared plus 4x plus 4 is another factor. And I also know that this is a trinomial square. And this is how you factor a trinomial square. Sorry. So remember, if it's a double factor, you still count it as 2 zeros. So there's my 3 zeros. X equals -3, x equals -2, x equals -2. Those are always counted twice when you're looking for your zeros. Let's do another example. So this time we're going to do a 5th degree polynomial. So I know there's 5 zeros. And when I graph that, I can see the real zeros where it actually crosses the x-axis. It crosses at 1. It sits on the axis at x equals 1. It crosses at -1, sorry, and it sits on the axis as x equals 1. So those are 3 zeros. I know then that I have 2 imaginary zeros because it only touches the x-axis 3 times. So to find the others, you're going to use synthetic division on each one of these, one right after the other, and we'll show you how that works. Okay, so I'm going to use that k value first and do synthetic division. You can go ahead and pause this if you want and do it on your own and see if you get the same thing I do. Remember then that this would be x to the 4th minus 4x cubed plus 9x squared minus 10x plus 4. It's a remainder of 0. I know that's one of the factors. Now I'm going to divide by that one. And again, pause this if you want to catch up and make sure that you got this as your result, which, as we know, this would be x to the third minus 3x squared plus 6x minus 4. Do one more, synthetic division using the other one. Go ahead and pause to see if that's what you got for your answer. And then, of course, this would be x squared minus 2x plus 4. But don't forget my other factors, because if these are my zeros, if my zeros are -1, 1, and 1, then I know one of my factors is x plus 1, x minus 1, and x minus 1. So now I have this thing. These are my 3 real zeros. There's 2 imaginary zeros in here, so I need to use the quadratic formula to solve this quadratic. I would pause this for right now. Just work it out on your own. Make sure you got that. So if that's what you get, 1 plus or minus the square root of 3i. Sorry, let me get some of this junk out of the way. So I know that the zeros of this function are 1, 1, -1, and 1 plus or minus the square root of 3i. Seriously, look at that. It takes up the whole page to do that. So you will be using some paper. Phew, we're done.